everyone. For this session, I'm going to talk about system tuning in GaussDB. I will first give some definition regarding the term system tuning. We will then look at a general procedure to follow when performing an optimization task. That will give us a structure to reason about some real-world problems that will be covered later. Specifically, we will diagnose performance issues in a systematic way. Then I will introduce a powerful tool called the WDR, which helps us to do exactly the works. So, what do we mean by system tuning? It's the performance optimization process in hardware, operation system, or database system. The aim is to make full use of the hardware resources such as CPU, memory, I/O, and networks. Also, we want to avoid contention between them. We will then have a system with higher throughput. As a type of system software, performance of databases can be affected by hardware in terms of the server itself, storage, and the network. Other factors could be substantial as well, such as in the system scale. It is the volume of data that access the database concurrently, and in software environment. It particularly means that the configuration parameter we set to the OS and the database setting, like the DB kernel parameter or the indexing strategy we use for a specific data model. Just take a look at the graph right here. It shows us, on top of the pyramid, it's the most hardware-oriented optimization, which is normally the most expensive and hardest to gain benefit from. On contrast, if we move downward, we get closer to the application logics. By experience, it's way easier to improve the performance and with lower costs. So, when we are setting up our databases, we would like to standardize the parts that are expensive to be optimized, like the hardware, networks, and operation system. We want to adopt the recommended setting to those parts so that we don't bother tuning their performance for the most of the application scenarios. Then our optimization work could just focus on the application system, the SQL statements, and the database system itself. But we are not talking about the SQL optimization here, since it's in another lesson. We will just focus on the system tuning. Having a big picture in mind, we will then look at a systematic way of doing such an optimization. In a general optimization process, we start by determining the scope. Is the whole system suffer from a performance degradation, or it's just a single application subsystem, or a single SQL clause? If it's the whole system, we will first indicate whether the pressure goes into the database. If it's not, we should analyze the application side. It can be the lack of server resources, slow queries in the app, or things like improper config on the connection pool, or even network latency between the server and the database. If the workload does reach the database, we could normally see that the utilization is high or abnormal usage for resources like CPU, memory, I/Os, or networks. Having an idea of the current resource utilization, we could then analyze for specific situation. There are a lot of reasons that can slow down the system, such as the concurrency issues, bad config to the database, insufficient allocated resources, bad SQL statements, and so on. For different types of problems, we use different approaches to diagnose and hopefully to solve them. We iterate the whole process until the performance metric meets the requirements of our application. Let's first confirm that the workload pressure indeed goes into the database. We do that by looking at the resource utilization numbers, including CPU, I/O, memory. You can check those as data visualization if you've got an operations platform. Otherwise, you could simply use the Linux command. Top for CPU, free for memory, IOstat for IOs, which are the ones we're familiar with. And the SAR commands right here give us the historical stats. And for the GaussDB database itself, we provide a view called the global thread pool status, and it's in the DB perf schema. It's to indicate the running threads and the active session numbers. They could be more intuitive to see if the database is currently on high workload. By experience, if the utilization percentage of CPU, memory, I/O are less than 50%, or we have an active session number that is way lower than the connection we request from the application, it means that the workload has not reached our database. Then we will need to focus on the app itself or the network link. Or if we really find that the database is the bottleneck, we will need to do optimization on the DB. Then we are going to look at the methods that we normally use from a few real-world examples. We first look at high CPU usage problems. In the beginning, again, we want to make sure that the CPU usage comes from the database. Here, we use the top command and rank the processes by their CPU percentage. In this picture, we can see a typical example of our database using a lot of CPUs. This information is real-time. If you would like to check the historical ones, as I mentioned, just use the SAR command by specifying the corresponding log file. High CPU usage of the database is normally caused by bad SQL execution. For example, there are no valid indexes for the query, or that it requires a lot of hard parsing. But how do we find those problematic SQL statements? One way is to analyze them with the unified SQL views. By means of unified SQL, the view classifies SQL statements with similar patterns into the same template and put together their statistics. For example, we have a SQL like select star from T1 where x equals 1. Then no matter what we expect x to be, we always put them into the same category. One of those views is called statement with the schema dbperf. It's where almost all views we cover today base in. It gives loads of information about the application in the SQL execution. As we can see in the picture right here, query is the SQL itself, and cause is the total number of execution. Total elapsed time is the accumulated execution time. Those two numbers allowed us to deduce the average time for that. We also have row-related stats like n-tuple fetch. It's the number of tuples by random search, and n-tuples return is the one by sequential search. Another one is the n-tuple return. Its number is large when we don't have a valid index. It can be that there's no index at all, or the index has been invalidated. We also provide a slow SQL view. Instead of the unified SQL template, it records the actual SQL that takes long time to execute. The WDR gives us similar information as above, but it's more intuitive and easy to use, and we will cover it later. Now, let's put our attention back to the stats number here. We see that the number of sequential scanning is excessively large here. So let's look at the table definition that we query on. And there's no index at all. By creating an index for the column we query the most, we eventually decrease the CPU usage in this scenario. Other cases are that the CPU usage is not due to our SQL statements. We could then use the full filing techniques to analyze the execution of our database. Specifically, we can use the perf tool to collect the runtime stack information, and by using tools, we could generate flaming graphs that give us the percentage of each time-consuming C functions in the database kernel. And the issues are really case by case if we really need profiling to analyze the system here. Okay, let's move on to the I/O problems. We enter the I/O stack command to check those numbers. Percentage means the I/O utilization in user mode. R await and W await means the latency time you need to wait for a single I/O read or write. If those numbers are large, then we have a bottleneck in our disk. By mean of large, it's the latency greater than 3 milliseconds for an SSD. We then use the I/O top command to see if it's the database threads that make such a consumption of I/Os. And from the picture, yes, we can see the top twos are the wall writer and page writer threads. They're responsible for flushing wall logs and the user data into disk. And it should be normal that they rank like this. But if we see that the TP worker thread consumes a lot of I/O, the system is then in trouble. Because it's the threads that serve our SQL query. There could be many reasons for that, like doing lots of physical read. To figure it out, we still need to query the wait event. We provide these views given exactly the information. For both real-time and historical data, if there's a bottleneck, we expect to see big numbers of data files read and write. Also, the wait I/O event. If it's our SQL statements that cause high I/O usage, there could normally be lots of physical reads. From the statement view down below, we query the mblocks fetch and the mBlock hit, and minus the number of fetch by the number of hit. We would then have the number of physical reads directly from the disk. We can rank them to properly find the problematic SQL. Given that we have a large number of physical reads, there could be a few reasons. The SQL execution might be ineffective in the sense that it scans a lot of rows. It could be the lack of indexes, or in a nested loop join, it puts the large table in the outer loop. If we use AStore for table storage, it can also be that the vacuum works have not been done on time, which led to a large number of dead tuples. Then we will need to scan a lot of usage pages. Or the buffer pool size is too small, so that we will need to do the page replacement frequently. In order to determine which one is the actual reason, normally we either look bottom-up, which means that we look at the numbers or the OS config like the RAID policy or the I/O scheduling algorithm. Or we look top-down, that is to focus on the abnormal physical reads, I/O duration, or wait events. which we can figure out in the database itself. I would surely recommend the second method. Before looking at diagnosis on the memory, I'm going to talk a bit on the memory model of GaussDB. Normally, we divide them into two large blocks, dynamic memory and shared memory. Dynamic memory is the memory resource that we use for any operation by the database kernel. We dynamically request memory from the OS because they are not pre-allocated in advance. There could be cases where the memory resource is not enough. We will then get an error by executing such kind of query. Another part we need to care is about the shared memory. They are primarily used for the actual user data in tables as a page buffers. The shared memory is pre-allocated. When we have too small shared memory space, we suffer from frequent data flushing to disk when it's not actually necessary. We will have an example when talking about WDR for this. The total amount of this memory is controlled by the parameter called mixed process memory. For other types of memory, as we can look up from the view called PG total memory detail, most of them either belongs to dynamic or shared memory. We don't normally care about the ones down below. In most scenarios, we care about several parameters related to memory. Workmem is the one used by query execution, like hash join or sorting operation. If we set it too small, we'll find this query to be executed quite slow, since they will need to flush the overfit data into the disk. Maintenance workmem is the memory used by maintenance operation like vacuum or indexing. And we also have C-store buffers and share buffers. They both belong to shared memory but used for different storage types. And the C-store buffers is for C-store. The another one is for A-store. When we have memory issues, we either get a prompted error saying that the memory resource is insufficient. That means dynamic memory is overly used. Or we have a slow system when executing a query over a large amount of data, which means that the buffer pool is too small. For the most scenarios, it's just the improper setting of the parameters in the last page. We would like to check those in the first place. Then we proceed to the SQL queries by looking up the following views. Sortmem use and hashmem use are the two columns that we query from. This gives us an idea of which query uses up the most dynamic memory. Then we might adjust the workmem and rewrite the queries for better memory visualization. If that doesn't solve our problems, we could also check the connection number that we set on the application side, since each connection takes a portion of memory. Too many of them will cause problems as well. Finally, we can go deep into the number of how the database uses those memory. We select a view share memory detail. It gives us how much memory is used for each internal memory context. This may give some hints of what's happening. Again, when we get into this state, the reasons of the problem is case by case. Let's look at an example of setting the parameter workmem to be too small. By explaining the execution plans of the targeted query, which we can get from the previous searching. We can see that there's a disk keyword in the sorting operation, which means that the sorting could not entirely fit into the memory and need to write temporary results into disk. We then readjust the workman parameter and explain the execution plan again. We find that it no longer writes into disk, and the performance problem has been solved. The next topic is about network autonomy. In most of the cases, network problems are about disconnection, high latency, or full bandwidth. Disconnection is quite normal when we just deploy a new application and haven't got the configuration correct. In that case, we will see that there's no workload on the database at all. While for high network latency, we get slow feedback on the application side from the database. But the execution time of SQL query is quite short. In that case, we can use the ping command to see that if the latency actually meets our expectation. The GaussDB requires less than 0.2 millisecond within an area zone, less than 2 milliseconds between different area zones, and less than 100 milliseconds between two regions. For problems where the network bandwidth is full, it happens when we have highly concurrent data transmission workload. We can confirm this by using the SAR command to check that if it really is the case. Here, the Rx kilobyte per second is the number of KBs being received, and the TX KBs is for transmission. Let's now move on to the concurrency-related problems. In the most scenario, it's just the log waiting problems caused by concurrent updates. Then we might see the latency growth. TPS decreases or the throughput would be full. There are a few ways to see this. V1. We can check the real-time events via the view called pgthreadWaitStatus. We focus on the log-related events. V2. This view called local active session gives us information like the wait event, log, and the execution state. It samples the execution query once per second. Note that this steps store in memory and hold 20,000 records for maximum. V3, a view called the GSASP, which is similar to the second one, but instead it samples 1 per 10 seconds and have those information persisting for 2 days by default. In the last slides, we gave you some views that you can query stuff about internal events, and here is a list of those events. I will point out several of them, but will not go through them one by one. None means just that the database is not waiting for anything and is running normally. Wait command means that the database is waiting for requests from the application. If you've got too many of those, the workload pressure haven't actually reached the database. Wait IO indicates that the IO-related events like disk read and write. A large number of these may say that your disk IO does not meet the requirement, or that the SQL execution is not optimal that causes unnecessary IO use. Flash data is the transmission event through the network. And the log control sleep is a special one. It's due to the flow control. By means of flow control, if you are in a primary and standby deployment, you have data from the primary database replicated to the standby. And sometimes, due to networks or execution efficiency, your standby instance might fail to catch up with the newest data with the primary. Then you will have slightly inconsistent version of data between the two nodes. In order to avoid this kind of inconsistency, we provide a mechanism called the log or flow control to force the primary instance waiting for the standby. In that kind of scenario, you might get a lot of log control events. And there's a parameter related to this. We will see that later. Regarding problems related to logs, normally application will receive error on log waiting timeout or just simply deadlock. In other cases where we have blocking session, we can again use the page's stat activity to query about information of blocking, like query ID, wait status, block session ID. Then we are able to queue the block session using the following system function called page terminate backend. We have talked about solving blocking problems in real time. Sometimes we have asynchronous problem, like we might find deadlock or locking timeout errors in our database system logs. To see those, we simply grab those keywords in our GS log. Then we will get the problematic queries and the thread ID that block it. Having those kind of information, we will use the view local active session or GSASP to query on the thread ID with a proper time interval. They give us something on the right hand side here, where we can find the blocked session ID. Then we might need to pay attention on it to see what kinds of query that block our execution. Let's take a look at the diagnosis on long transaction, which simply means a long running session. It doesn't terminate in a short time or worse, doesn't terminate at all. It causes problems like the uncontrolled expansion of tablespace or warlog. In order to proceed a long transaction that affects the database performance, first, we use the following queries to find the transaction that have already executed longer than 1 minute. Or it's caused by the log issues, we will use the second query instead, which joins the information of the long-running session with blocking information in the PG thread wait status in order to get the session that block it. Like the previous example, we use the terminate session functions to queue it. Then our long-running transaction get released. In the final section, we're gonna introduce a novel tool that allow people to do performance analysis easier on GaussDB. It integrates all the stuff that we have been talking about and provides a user-friendly interface, which we can easily interact with, as we will see. WDR stands for Workload Diagnosis Report. It's an efficient tool to collect and analyze performance statistics. It's a bit similar to the AWR in Oracle. Effectively, it provides the usage information of the whole database system within a specific time interval. We can then easily deduce the healthiness of the database from the report. In order to generate those information, It periodically creates a snapshot of various metrics regarding to the database dynamics, and they get inserted into the system table, from which we are able to generate a report from two separate WDR snapshots. By default, the snapshots are taken every hour and retained for 8 days. Down to the report types, we can view them in either cluster or node level. In the report summary, we've got loads of information, which I will not go through one by one, but normally we should pay attention to several of them. The first one is the top 10 wait events. It should be intuitive to see what kinds of events that the database wait on the most. And the time model is yet another way to see what kinds of execution the database spends the most time on. And the buffer hit ratio, it reflects that if we have good data locality when doing the execution. Then, as a user, here's the way to generate an WDR report. If you have a visualized maintenance platform, you may be able to achieve that by just clicking a button. But this is the command line way. We connect the system database named Postgres using the GSQL tool. We may wish to query the snapshot beforehand through a view called snapshot in the snapshot schema. Or if we haven't got enough snapshot yet, as I said that 2 is required, we need to select a create WDR snapshot function to actually create them. Then we just follow the steps, the \A and \T and \O, where we need to specify a file name. Finally, we run the generate WDR report system function to do the work. We need to specify the beginning and ending snapshot ID, report types, report scope, and node name. If we choose to only view one of the nodes in the database cluster, we can omit the final parameter. We are then going to go through the GUC parameters and restrictions on the WDR tool. For GUC, we have the enable WDR snapshot. It simply controls whether we are using the WDR, and it's on by default. And we can set how frequent the database takes snapshots of its performance metric number. There is another one called the WDR snapshot retention days. It allowed us to specify the duration that we would like to keep the WDR snapshot on disk. In short, we still got a few restrictions. This no node restart is allowed between 2 snapshots, and we should not perform job database between 2 snapshots. And also, if you have performed active and standby switchover between 2 snapshots, we cannot snag them to create an WDR report. For the last one, you cannot reset the dbeperf.statement view because that's where our information based in. We're now ready to look at some data reported by the WDR. On the right-hand side, there's a brief summary of the database performance. We should be interested in the P8095 latency down here. They reflect the responsiveness of the entire system in most of the time. If they meet the application requirements, then the system is healthy. And we have the top 200 SQL query ranked by different aspects like elapsed time, CPU, and physical reads. We may want to click on those to see queries that consume specific type of resource or with certain running characteristics. Let's go through a few examples. The first one is to diagnose by using the top SQL information. In the case down here, someone is doing a load test on the service, and the result doesn't appear as we expected. Using the top commands in console, we can see that the CPU was fully occupied. In the WDR report, we then click on the SQL ranking by CPU time. Then we check other metrics of this top CPU time queries. We can see that they've got a large number of tuple returns, which effectively means physical reads. We suspect that the relation doesn't have a proper index for this kind of query, and we check the structural definition of it. It turns out there's no index at all. After we create a corresponding index for this case, the performance issue got solved. Okay, let's look at an example about the buffer hit rate. The scenario we come across again is that database performance fails to meet the requirement. We generated WDR by selecting snapshots during the load test. And this time, we check the instant efficiency percentage session, which is also some sort of brief summary that we recommended to browse for common problems. From the chart below, we can see that the buffer hit rate was 76.7%, which you might consider as already decent for a database, but actually, we see that as an anomaly. In a healthy system, especially for transactional type of workload, we advise a hit rate higher than 97% so that it will not be the bottleneck. Then we're gonna deal with the problems of low buffer hit rate. On that, we normally consider two reasons. The first one is that the most common one, and it's the parameter called share buffers is set too small. Or you might have some SQL query that do full scan on large tables, which is not normal for transactional workload. We check the share buffer parameters in the database, and the size was 50 megabytes. It's apparently too small. We reset that to an appropriate value and solve the performance problem. Let's then continue with another one about the abnormal wait event. We have performance issues again. The things different from the previous one is that we have low database usage of resources like CPU, I/O, and memory. We could read that from the console. But in the WDR report generated, we check the top 10 events ranked by total time. We see some wall events takes the top 2 places. They're considered normal, but not for the third one, the log control. In this case, we have a large portion of time where the primary instance is waiting for the standby to catch up, but not processing new requests, which is not good. For cases where log control is frequently invoked, it can be that a related parameter specifically for this behavior is not properly set, or that we might have network link problems between two nodes, or just that the standby nodes machine has got bad I/O performance that slow down the warlog replay. We check the parameter called the recovery time target, which is an approximate value that if we suffer from a failure on the current node, the time in seconds that we need to recover to state that the data is consistent, and the database is able to accept new requests. In this case, the volume of that is 60, which could be too small depending on the environment that it deploys. In this scenario, we rather set it to 0, which effectively shut down for this kind of mechanism. And we retest the system and found that the performance condition was met again. It's for sure that you may not want to turn off the log control mechanism that prevents you from long disaster recovery and replica inconsistency. In practice, you want to pick a value that balances the real-time performance and things like recovery time and consistency. Finally, we will look at an example on the time model. The time model value reflects how the database execution time distributes among different stages. The scenario we've got problem with is doing data batch and deletion in parallel. We check the time model selection of the WDR reports that we produce. DB time is the total time, which should rank at the top. And because it's a transactional kind of workload, we have CPU time as the second, which actually includes the plan time. It's at the third. And it indicates time that we spend on generating execution plans. We've already known that it's a batching workload, which means that we repeatedly execute almost the same operation. We don't expect the plan time to be this high. Empirically speaking, it's caused by not using the PBE that stands for pass by execute in the database. So the database couldn't reuse the same plan for similar execution. We should check our code on the application. Another possibility that we have is the parameter plan cache mode being set to the false custom plan option, which would prevent us from reusing the same plan as well. By default, the parameter is something called the plan cache mode auto. We can just leave it as it was for most of the cases. Okay, now we are in the summary. In the very beginning, I give a definition of system tuning regarding the different types of hardware resources that the database relies on. Then we went through a general optimization framework, which we would like to follow when dealing with any performance issues on the system. We use that kind of methodology to diagnose real-world problems related to abnormal use of CPU, memory, disk, and so on. For each kind of scenario, we query different system tables or views to dig out the root cause. And correspondingly, we adopt solutions from our experience, which solve the performance issues that we might come across in common. After that, we introduce the WDR tool that integrates this knowledge into a visualized and interactive HTML report, which should give you some ideas during a system tuning process. On the slide here, we classify the possible performance flaws that occurs in different aspects, such as the ones happens in hardware, database kernel level, and some of them relate to the cluster behavior like primary and standby. You might want to check this as well when tuning a system. In the final sections, we're going to look at a few test questions. The first one is asking which of the following methods are used to query the SQL statement with high CPU consumption in GaussDB. And the answer is A, B, C, so all of them. And the second one is which of the following parameters control the size of share cache and the row storage of the database in GaussDB? And the answer is B, the share buffers. The third one is which of the following wait events has a high proportion, indicating that database frequently trigger flow control, which limits the host performance? And the answer is C. Flow control is just another name for load control. And for the final one, it's asking if it's a true statement. By default, GaussDB WDR report snapshot are retained for 7 days. And the answer is B, false. As we can see from the previous slides, they are retained for 8 days by default. Okay, that's pretty much all of the contents I'm going to cover in this session. And thank you so much.